Okay, so the similarity transformation, has this form. Okay, so we have some matrix in the middle, and then we multiply some matrix on the right and the left, and one of them is inverse of the other. Okay, so in this case, we are multiplying P of an inverse on the right, and then multiplying a P on the left of the same matrix. So that is the that is called the similarity matrix. And then if some matrix B can be computed by this transformation, for example, and then we call A is similar to B. Okay, and also the important characteristic of the similarity transformation is that the eigenvalues of A and B doesn't change, so they remain the same. So as we saw earlier, they have exact same characteristic polynomial. So that way, the characteristic polynomial gives the same equation and the solutions for our eigenvalues of lambdas, right? So that was the meaning of this similarity transformation. And then using the similarity transformation, in this chapter 5.3, we learn about this diagonalization. So diagonalization means, diagonalization means we can represent an input matrix A in the form of a similarity transformation, but that similarity transformation can be represented as this form, where the matrix D is diagonal matrix. Okay, so here we are still handling this square matrix of an n by the size of an n by n, and then here the P has the same size of n by n, and then D also has the same size, and also the P inverse, of course, has the size of an n by n. So here P can have any other size, but in this case we have to have this P inverse to be able to define this similarity transformation. So the inverse is only defined for the square matrix, of course. So P has to be the square matrix. So altogether A and D should have the same size. And then originally A also has a square matrix, because we are talking about this eigenvalue and eigenvector. And then this eigenvalue and vector are only defined or considered only for those square matrices. So A is a square, and the similar matrix D is also square, and also P and P inverse is also square matrix that has the same size. But here, when talking about the diagonalization, what is diagonalized? This matrix D is diagonal matrix, and that's when we call this as a diagonalizable matrix, or diagonalizable relationships between A and D. So here, the matrix D will only have the diagonal entries not as non-zeros, but the zeros on the off-diagonal part. Okay. So diagonalizable means the matrix A is similar to matrix D, which is a diagonal, through some matrix P and P inverse. Okay, so when we can find at least one P that satisfies this relationship, that changes A into the diagonal matrix D, then we call this as a diagonalizable matrix A. Okay. And in this case of a diagonalizable matrix A, and in this case, this matrix A has an interesting relationship. So A squared, or in general, A to the power of K can be represented as P. Yeah, so let's start with this A squared, and then PD P inverse, and then PD P inverse. And here P inverse and P can be cancelled out, and then it can be represented as PD squared P inverse. And here P squared can be represented in a very simple form. So if P was 3002, if D was this matrix, and then D squared will be simply 3 squared, 2 squared, and 0, 0. So here D squared can be very efficiently or simply computed in this form. And then A to the power of K can be also represented in a similar manner. So P times D to the power of K and P inverse, and D to the power of K will be, in this case, 3 to the power of K and 2 to the power of K, and 0, 0. Okay? Okay, and then let's discuss about this diagonalization theorem, and probably this will be the only part that we will learn today, I think. So yeah, let's try to understand this carefully. So this diagonalizable matrix A, or this kind of relationship between A and D, this diagonalizable representation, or diagonalizable matrix A, has the relationship with the eigenvalue and eigenvectors. Okay, so here, what is the problem? So the problem is we have to find at least one P, right, that satisfies this equation, and also the resulting D. So these two parts are what we have to find, and these matrices P and D are actually made or created by your eigenvector and eigenvalues. Okay, so the relationship between this equation and also the eigenvector and eigenvalue. So that relationship is the key point that we have to study today. Okay. So this theorem is very long, but yeah, let's decompose it into two parts. So the first part is the main theorem, and then the second part is additional explanation about this theorem. Okay, so let's first focus on the first part of the theorem. So the first part of this theorem says, so we are given a square matrix of n by n size, and this matrix is diagonalizable if and only if A has n linearly independent eigenvectors. Okay. So last time we learned something called algebraic multiplicity and geometric multiplicity, right? And then, yeah, if we recall that, so we first consider this determinant of A minus lambda I, and then in this case, so let's consider our determinant characteristic polynomial in this form, okay? Okay, so let's have a multiplicity as 3 for this. Yeah, so let's have 4. Let's have 4 for this term, and then we consider this algebraic multiplicity and geometric multiplicity, and then the root for this lambda, right? So in case of lambda being 1, and then algebraic multiplicity was 2, and then the lambda being 3, and then that will have a multiplicity of 4, and then this will have multiplicity of 1. Okay, and then this geometric multiplicity, what was that? So the meaning of geometric multiplicity was the number, basically the dimension of the null space, or that null space was called eigenspace. Okay, so in this case, since lambda is 1, so we can consider this homogeneous linear system when lambda is set as 1. Okay, and then in this case, the dimension of this null space, and that dimension is this geometric multiplicity. And we learned that this geometric multiplicity is at least greater than or equal to 1. So it cannot be 0, because in that case, I mean, if the dimension of this null space is 0, and then that means we only have a trivial solution, right? But by definition, or from this relation, requirement, saying this determinant of a minus lambda I being 0, and in that case, for whatever lambda satisfying this equation, that should at least give us at least one dimensions for our null space. So these values should be greater than or equal to 1, but also they cannot exceed this algebraic multiplicity, but they can be the same. So in this case, yeah, so we can have this conditions in terms of the geometric multiplicity. Okay. Okay, so in this case, we have 2, 4, and 1, and that means the size of a matrix A is 7 by 7, right? Because this degree of this polynomial is the same as the matrix size. So in total, it will always give 7, which is the same as the matrix size all the time. But in terms of the total sum of this geometric multiplicity, it can be less than 7, right? And also it can be more than or equal to 3. Okay, in terms of the summation of these 3 numbers. Okay, and here in this relationship, so back to this diagonalizable thing. Okay, so when is your matrix A diagonalizable? This theorem says you have n linearly independent eigenvectors, and that's when your matrix is diagonalizable. Okay, and in terms of this geometric multiplicity, so here n is 7, and when do you have n linearly independent eigenvectors? And that's when you achieve the maximum values at for each of your root of this lambda. Okay, so when you achieve the maximum value, okay, so which means you have the maximum geometric multiplicity, or you have n linearly independent eigenvectors, and that's when your matrix A is diagonalizable. Okay, so that's the kind of a conclusion or the main message of this theorem 5. Okay, and let's understand why that should be true. So So when talking about this relationship, we can convert this representation into this form. Right? P inverse, we can just multiply P inverse on the right, and then we obtain this, right? But in this case, can we go back to this original equation? So is it always true, having this direction? So it's not always true, and when is it not true? Right. So here we can always go from the left to the right, but we cannot always go from the right to the left, because here we lose, or here we no longer have the assumption that P is invariable, right? So when writing this equation, you don't know whether P inverse exists or not, right? And also, in this case, we talked about the size of the matrix in terms of, as this form, right? So since P is invariable matrix, P should be square matrix, right? And then all the size of P and D and P inverse should have the same size as the size of an A, right? So all the matrices that you see, A, P, D, P inverse, they should all be n by n. Okay, but in this equation, so let me tell you one interesting thing. In this equation, A should be the square matrix, of course, because A is just an input matrix. I mean, predetermined matrix that we are given. And also the matrix, but in this case, P and D is no longer need to be, they don't need to be square matrix anymore in this case. Okay, and then you can construct this matrix P and D by using your eigenvalue and eigenvectors. Okay, so let me show how. So in conclusion, the matrix P should be your the collection of your eigenvectors, and the matrix D should be the collection of your eigenvalues. And by putting or plugging in those eigenvalue and eigenvectors, and then you can construct this matrix P and D. So let's start with this. So suppose you found one pair of eigenvector and eigenvalue that satisfies this equation. Okay, and then suppose you found another one. Okay, in this form. Okay, so v1 and v2 are two different vectors, and then lambda 1 and 2 are the two different eigenvalues that are associated with v1 and v2 respectively. And in this case, you have two different equations, but you can assemble them into one equation in this form. Okay, so you just collect your eigenvectors in here. So v1 and v2 are your eigenvectors. Okay, and then the same matrix P, which is your set of eigenvectors, and then you construct a matrix D. So D was a diagonal matrix, and then how you construct these diagonal entries is in this form. So lambda 1 and lambda 2, and then 0 and 0. Okay? So in this case, as I mentioned, your matrix P and D is no longer a square matrix. So suppose A was 7 by 7 matrix, and then A will have this 7 by 7, okay? And then each of your eigenvectors will have also the seven-dimensional vectors, right? So V1 and V2 will have this form, and this one will be your matrix P, okay? And then P will have the size of 7 by 2, right? And then also this V1 and V2, and then lambda 1 and lambda 2. So in this case, this is a 2 by 2, and this will have the size of 2. This P will have 7 by 2, and this part will have 2 by 2. Okay. So you can assemble these two into this one single matrix equation. Okay. So here, let's try to understand why these two equations will be the same as this one single matrix equation. Okay. So when thinking about the left-hand side, and then this will be the same as AV1 and AV2. Okay. So you could, if you imagine the matrix multiplication, and then you will compute the inner product with this row and this column, and then you will form just one entry here, and then move on to the second row, and then compute the inner product with the same column. Okay, that will form the second entry here. Okay, and so on, right? So that way you will have one single matrix, one single column vector, and then you move on to the second column, and then you will do the same inner product starting with the first row of matrix A, and then you compute the inner product with this, and then that will form this entry, right? Okay, and then that way you will form this two columns, and each of these columns can be represented as AV1 and AV2. Okay, and then let's consider this right hand side. In the right hand side, we learned we learned how to interpret this. Okay, so we have these two columns, and then we have the matrix on the right, and then each of these columns will work as a linear combination coefficient that mix and matches between these two columns, right? And that linear combination coefficient was these two values, and here in the first column we'll have the lambda 1 and 0, and that will result in lambda 1 times V1, okay, and 0 times V2, okay, and then so altogether this part will form one single column, right? So that is a scalar multiple of the V1 with the scalar of lambda 1, and then the second part, or the second column, will have this linear combination coefficient, and 0 times V1 and lambda 2 times V2. Okay, so that will form this second column. Okay, so so this is a PD, and if we compare these two matrices of AP and PD, each of these entries should be the same, and thus the first column should be the same as the first column on the right, and the first column on the left should be the same as first column on the right. So altogether, AV1 should be equal to lambda 1 V1, and AV2 should be equal to lambda 2 V2. Okay? So that way, from these two separate equations, we can construct one single equation that will cover up that that contains all the multiple eigenvalue and vector equations that we obtained. Okay. Okay. And from here, let's go back to this diagonalizable thing. So in this case of diagonalizable thing, the main point is that we have to have P inverse. Okay. So here, yeah, let's get back to this guy. So suppose we only have these two pairs of eigenvalue and eigenvectors, and then we have no problem in constructing this AP equals PD, just like this, right? We just constructed this form, right? But in this case, until this point, at this point, we cannot go back to this PD P inverse. And why? Why can we not go back to this PD P inverse? The reason is because we don't have P inverse yet, right? Why don't we have a P inverse? Because we didn't even have a square matrix yet. So here, as I mentioned, P and P inverse should be square matrix. But up to this point, as I mentioned, in terms of the size of the matrix, P is only 7 by 2 because we only have 2 eigenvectors. Okay? And then when do we have this square matrix? Okay, so this dimension, the number of rows will always be the same as 7. So this will not change, right? And then when we have this matrix P as a square matrix is when we have 7 different eigenvectors. Okay? Okay, and then suppose we have like a 7 different eigenvectors. So it's like AV1 equals lambda V1, lambda 1 V1, and then all the way through the AV7 equals lambda 7 V7. Okay, suppose we have this 7 different equations, and then we can put together all these V1 through V7 as one matrix of P, and that will now have the square size of 7 by 7, and then accordingly this P times D will also have the diagonal matrix of the size of 7 by 7. Okay, and now we have this, at least have this square matrix of 7 by 7 for P and D. Okay, and then if P is invertible, and that means our eigenvectors should be all linearly independent. Okay, so we constructed at least this 7 by 7 matrix. Okay, and then this matrix P, so that this matrix P can be invertible, and then it means each column of P should be linearly independent, right? And that means we have 7 eigenvectors, and all the 7 eigenvectors are linearly independent. So that is the condition that allows us to go back from the right hand side to the left hand side. Okay. Okay, so that's why we have this theorem 5. So n by n matrix A is diagonalizable, and that's equivalent to saying A has n linearly independent eigenvectors. Okay. And then we are ready to move on to the second part or second paragraph. But second paragraph doesn't give you no new information. So it's basically a restatement of the same thing that we just learned in this example. Okay, so let's read these. So in fact, it's like an additional explanation. It's not about the main. It's not about the main power of this theorem 5. So in fact, if A is diagonalizable, and then it is the same as this A equals PD P inverse, for some matrix P and D. Okay, and then let's see. In this case, the diagonal entries of D are eigenvalues, and the columns of P will be the eigenvectors. Okay, so that is this additional explanation. Okay, so here the this part, I mean the second part, is saying the following thing. So suppose you didn't compute any eigenvalues and eigenvectors. Okay, and then instead someone gave you the matrix P and a diagonal matrix D, and P is also invariable, and these P and D is satisfying this equation, A equals P D P inverse. Okay, so in that case, this second paragraph says each columns of P that someone gave you. Okay, so again the situation is someone gave you P and D, and then even before you compute this eigenvalue and eigenvectors, sorry about that. Yeah, even before you compute the eigenvalue and eigenvectors, and then automatically your matrix P and D will give you a set of eigenvalues and eigenvectors. Okay, so that is what this second paragraph is saying. So you shouldn't be confused about this second part. Okay. And how we understand why the second paragraph should be true is really the same as this relationship. Okay, so in this case we started from these, the equations of eigenvalues and eigenvectors, and then we constructed this relationship. But now let's consider the situation where we are given this AP and PD, or this guy, A equals PD P inverse, and suppose you are given this matrix P and D, and then you can easily change it into AP and PD, right? And then we obtain this, right? And then this one will still be the same. This one still will be represented in this form, AV1 and AV2. But here, V1 and V2 are not yet your eigenvectors, right? So they are not yet your eigenvectors, but these are just computed from this matrix A and the first column of matrix P. Okay, so again the situation is someone gave you P and D separately, even before we know they are eigenvector and eigenvalues. Okay, and in this case these are still the true. Okay, so we can still represent these guys into these forms, right? And then AV1, which is the first column, should be the same as this guy, lambda 1 V1, right? So by setting these first columns from the left and right, we can obtain this first equation for this eigenvector and value pair. Okay, so that way, initially we started from these eigenvalue and vector equations and then obtained these relationships, but we can kind of change the direction reversely in this manner. So we obtain this guy, and then this will still be the same, and then that will give you this eigenvalue vector equations. Okay. Okay, up to this point, any questions about this theorem? Okay, so yeah, although it may sound boring because I'm telling you the same thing over and over, but since this is a really important part, so let me just summarize for the last time. So here, your matrix A is diagonalizable, which means you can obtain this equation, where P is invertible matrix and D is diagonal matrix. Okay, so that's the meaning of the diagonalizable matrix A. Okay, so A is diagonalizable, and then that means, or that is the same as the situation where you have n linearly independent eigenvectors. Okay, so that allows you to form the square matrix of this P, and linearly independent columns will give you P inverse or invertible P. And also in terms of the geometric multiplicity, and that's achieved when you obtain the maximum possible number of eigenvectors, or the maximum dimensions of each of your eigenspaces. Okay. Let's see. So let me briefly check the example. So the question is, or the task is to diagonalize some matrix A. Okay, and then this task boils down to obtain or compute eigenvalues and eigenvectors. Okay, and then you form this AP equals PD by just aligning your eigenvectors in this form, and then eigenvalues in this diagonal entries in D. Okay, and then you try to obtain n linearly eigenvectors and value pairs, and in that case, your matrix can be diagonalizable, and then you will obtain this A equals PD P inverse. But if you cannot obtain n linearly independent eigenvectors, and then you can conclude that your matrix A is not diagonalizable. Okay. So the first step. So here, so the main task is still the same. So we have to compute all the possible pairs of eigenvalues and eigenvectors. So the first step is to compute this eigenvalues. So we construct this polynomial, the characteristic polynomial, and then solve this equation, and then obtain these. And so here we can see that algebraic multiplicity and geometric multiplicity, so for this algebraic multiplicity, it will have 1, because we see here as a 1 as an exponent, and then 2 here. Okay, and then we have to check. So it will be just 1, right? So it will definitely 1, because it will be at least 1, and then it's also bounded by 1. And then in the case of these guys, it can be either 1 or 2. Okay. Okay, so we plug lambda first as 1, and then we solve this guy. So 1 times I, x equals 0, and then you just compute this the solution for the homogeneous linear system, and then obtain the parametric vector form, and then you obtain the basis, and this is one basis that we obtained. And then in the case of lambda being -2, and that had the algebraic multiplicity of 2, so that's the case where we have to be careful, because it can either give you only 1 eigenvector or 2 eigenvectors. So in the case of just one, in case it will only give just 1 eigenvectors, and then we cannot achieve this diagonalizable matrix A, because it does not have a n linearly independent eigenvectors. But if it gives 2 eigenvectors, and then it achieved this maximum number of eigenvectors, and thus altogether the dimension, or the number of linearly independent eigenvectors will be 3, which is an n. Okay, so if we plug lambda as -2, and then we compute this homogeneous linear system and then obtain the parametric vector form, and then fortunately it gave these two bases for the null space, and so we obtained 1 here and 2 here, and thus altogether we obtained 3 linearly eigenvectors. Okay, so we can conclude that they are, or the matrix A is diagonalizable. Okay, and then how we can compute this P and D is just simply aligning those 3 eigenvectors as a column vectors in this form, and that's how we obtain this P. And then for D, we just place these corresponding eigen values in this form. Okay, so that's how we diagonalize the input matrix A. Okay, so we can evaluate PD and AP, and then verify they are the same. And in terms of P inverse, we can compute the inverse of this guy, because we already obtained P as these 3 column vectors for the eigenvectors. Okay. Okay. And in this, let's look at this example a little bit more carefully. So here, so we obtained these 3 eigenvectors, and then we concluded that these 3 vectors are linearly independent, right? But how do we know this eigenvector and these 2 eigenvectors are linearly independent? So here we didn't do anything to check whether they are linearly independent or not, right? So here the question is, so we started from the different eigenvalues, and then each of these different eigenvalues gave these different sets of eigenvectors, and they are linearly independent. Okay, and the reason why they are linearly independent is because these 2 eigenvalues are the different ones. Okay. So as we recall what we learned last time, so suppose we have 2 different eigenvalues, just like this case. So we have lambda as 1 and lambda as -2, and each one will give its own set of eigenvectors. Okay, and those eigenvectors, those 2 sets of eigenvectors are always linearly independent, right? So that's what we learned last time, right? So here we don't need to check whether these 2 sets of eigenvectors are linearly independent or not, because they are always linearly independent, and the reason is because they are generated from different eigenvalues. Okay. Okay, let's check the theorem saying that, okay, it was in chapter 5.1, I guess. Yeah, so this was chapter 5.1, and in this theorem 2, we learned this relationship where we have all the different eigenvalues. So they are different values, and then these eigenvectors from V1 through Vr were generated from each of these different eigenvalues, and then they were always linearly independent. So that was the main point of this theorem too. Okay. And so in this case, these two are different eigenvalues, and thus these two sets of eigenvectors are always linearly independent. Okay, and then within each set, for example, in this case, it was generated from this homogeneous linear system, and then these two vectors were generated from computing our solution as parametric vector form. And then each of these vectors that were generated from the parametric vector form were always linearly independent with each other. Okay, so within each set, they are linearly independent, and between different sets, they are also linearly independent. So altogether, even if we collect all of them, they are always linearly independent as well. Okay, so that's why. Yeah, so that's why when we only achieve, so if we achieve these maximum number of the maximum number of eigenvectors, or in other words, in case we achieve this maximum number of geometric multiplicity, I mean, so suppose we obtain these two different eigenvectors and four different eigenvectors and one eigenvector here, but in order to we obtain seven linearly independent eigenvectors, even when combined all these eigenvectors together. Okay, so even when combining all of them into one set, they are always linearly independent, because within each set of eigenvectors, they are linearly independent, and then between these two different sets, they are also linearly independent because they are generated from different eigenvalues. Okay. Okay, and then let's move on to this theorem 6. And this theorem 6 is really easy once you understood all the things, what I just highlighted or emphasized. So suppose we have, we are given n by n matrix, but here in this case, n distinct eigenvalues. So in this case, let me ask this question. So what is the algebraic multiplicity of each of these n distinct eigenvalues? Okay, so let me ask again. So you are given, for example, like a 4 by 4 matrix. And then here the assumption is that you have 4 different eigenvalues. Okay, 4 different eigenvalues. And then what should be the algebraic multiplicity of each eigenvalues? Anyone can answer? Okay, so we have 4 by 4 matrix, and then this characteristic polynomial will always have the degree of 4. So fourth order polynomial. And then it is saying that we have 4 different roots or the solutions, 4 different values for our eigen values satisfying this equation. And then suppose that eigenvalue was 2, 3, minus 1, minus 5. And then what should be the algebraic multiplicity for each of these eigenvalues? It should be just 1, right? Why? Why? So this one is fourth order polynomial in terms of lambda. So it will have some kind of this form. A minus lambda and B minus lambda and C minus lambda and D minus lambda. Okay? So this one is one form of a factorization of your fourth order polynomial. And then the fact that we have all the different A, B, C, D, and then they should always have the power of 1 here. Okay? So in this case, in case A and B were the same as 2, for example, and that's when we obtain this algebraic multiplicity as 2. So here the maximum number of, here the total number of roots will always have 4. Okay? And then we have 4 different roots that satisfies this equation. And that means each of these powers will always be 1. So that means we will have always this algebraic multiplicity as 1. And then what should be the geometric multiplicity in this case? It should all be 1 as well, because it is at least 1, right? Because it's all having a non-trivial solution. And also it's bounded by this algebraic multiplicity, right? So that way we always have the geometric multiplicity as 1, okay? So altogether the summation of all these will also be n, or 4, okay? And also between these eigenvectors, they will be linearly independent because they were generated from different eigenvalues. Okay? So automatically, once you have, if you have n different eigenvalues, and then you will automatically have n linearly independent eigenvectors. Okay? So since you have n linearly independent eigenvectors, and then your matrix A can be diagonalizable. Okay, so that is this theorem. Theorem 6. Here in this case, it is not it's not always necessary. So it means this is not the only condition. So even when you have less than n distinct eigenvalues, and then you still have a hope to have your matrix A still be diagonalizable, which means like in this case. So in this case, we had like these algebraic multiplicity as 2, 4, which means in this case, what was the degree of your characteristic polynomial? It was 7, right? But you only have 3 different eigenvalues, right? But in this case, still you can achieve the diagonalizable matrix A, right? So you still have to check whether you achieve this maximum number of geometric multiplicities. Okay, so that's the point of this bullet. And so it's not this necessary condition, but it's also instead it's a sufficient condition. Okay. Okay, so theorem 7 is probably the last one, but yeah, I think we covered all of them already. Okay, so yeah, let's read through them. The dimension of the eigenspace corresponding to the lambda k is less than or equal to the this is an algebraic multiplicity that I mentioned. Okay, so it means, so what was the dimension of this eigenspace? So that was called geometric multiplicity. So geometric multiplicity is always small, equal to or less than the algebraic multiplicity. And then your matrix A is diagonalizable when the summation of the dimensions of the eigenspace is equal to n. And this happens, or this is equivalent to the situation where the characteristic polynomial factors completely into the linear factors. So this one gives you two conditions. So this one describes two conditions. Okay, so you have to satisfy these two conditions so that your matrix A can be diagonalizable. So the first one is this guy. The characteristic polynomial factors completely into linear factors. Okay, so this means, actually I myself had a hard time in understanding this. Okay, so this is written in a little bit of a tricky way, but simply this one is telling you that nth order characteristic polynomial should have n number of real solutions or real roots. Okay, so in this, so let's use the new. So we are talking about the same polynomial, characteristic polynomial, but in this case, suppose n was 4, but in this case, as we learned in the high school, it can have like some number of complex roots, not always having like a 4 different real roots, right? So suppose you have like this, 1 plus 3i minus lambda and 1 minus 3i minus lambda. So this is the situation where you have like complex roots, but altogether both the real roots and the complex roots, the total number of the roots should always be 4, right? But in this case, when talking about this eigenvalues and eigenvectors, we only talk about the real values. Okay, only the real values is possible for your eigenvalues. Okay, so in this case, we consider we only have two eigenvalues in this case. Okay, so in this case, in this table, the total number of these values will never achieve the total. In this case, the total number of these algebraic multiplicity will not achieve this the number n. So in this case, when we have like two complex roots, and then the total number of these algebraic multiplicities will only be 5. Okay, so in this case, you don't even need to check about your geometric multiplicity. Okay, so your matrix is never diagonalizable. So it's not diagonalizable because you don't have 7 different eigenvalues. Okay, because you have complex root, which is not considered as eigenvalues. Okay. Okay. 네. 매트릭스의
엘리먼트가 모두 리얼 넘버구나 하면은 항상 컴플렉스 루트가 나올 경우가 없지 않나요?
있어요. 왜 있냐면, 그러니까 매트릭스 A가 리얼 밸류를 하더라도요. 그러니까 우리가 그러니까 컴플렉스 매트리스는 우리가 그러니까 컴플렉스 도메인, 그러니까 그 복소수 쪽은 우리가 다루지를 않아요, 아예. 그러니까 이제 우리는 항상 실수인 경우만 다루게 되고, 실수인 경우에도, 그러니까 매트리스의 모든 엘리먼트가 다 실수인 경우에도 캐릭터리스틱 폴리노미얼은 저기 복소수인 근을 가질 수가 있어요.
근데 디터미넌트를 구하는 과정에서요.
네,
더하고 빼고 뭐 멀티플리케이션 하는 거밖에 없잖아요.
네.
그런데도 컴플렉스 루트가 나오잖아요.
아마 있을 거라고 생각이 들어요. 그러니까 네, 기본적으로 1, 2, 3, 4, 5, 6, 7, 8, 9 이렇게 9 이런 매트리스에서 여기서 이제 램다를 빼갖고 이거에 대한 디터미넌트를 구하잖아요. 그러면 이거에 대한 폴리노미얼은 3차 방정식이 돼요. 그죠? 3차 방정식이 되지만 코에피션트가 실수라고 해서 근이 꼭 실수인 건 아니죠. 근이 허수일 수도 있죠. 그러니까 뭐 알죠? 뭐 이렇게 그려주면 이거는 한 점만 만나니까. 그래서 실수, 총 n개의 실수근을 가지어야 일단은 첫 번째 조건이 만족이 되고, 그게 첫 번째 이야기예요. Characteristic polynomial factors completely into linear factors라는 이야기는, linear factors는 이게 실수의 형태로 뭐 램다 빼기 뭐 이런 형태로 이런 실수가 총 n개 텀이 나온다. Okay, so the first condition gives you the n number of real values for eigen values. Okay, and then the second condition is whether your geometric multiplicity achieve the maximum possible number, which is the same as algebraic multiplicity. Okay, so verbally the dimension of the eigenspace for each lambda k should be equal to the algebraic multiplicity. So again, this is algebraic multiplicity of lambda k. So for each of these so here each lambda k, you should achieve the maximum number of geometric multiplicity. So that's when your matrix A is diagonalizable. Okay. Okay. So so the last part. Okay. So this is the very last slide. Although I added blank slide at the end, but anyways, so A is diagonalizable, and BK is the basis for the eigenspace corresponding to BK for each K. Then the total collection of vectors in the set of these forms an eigenvector basis for Rn. Okay, so yeah, this one is also very long sentence, but the main point of this bullet item C is simple. So suppose your matrix A is diagonalizable, and then it means you have n linearly independent eigenvectors, right? So n linearly independent eigenvectors will completely span Rn. So it means your eigenvectors will cover up your entire space Rn. Okay? And then you can consider this set of n linearly eigenvectors as a new basis that represents any point in Rn. Okay, so let's use the example. So suppose A is 4 by 4. So suppose A is diagonalizable. And that means, so you computed lambda as maybe 2 and 3 and minus 1, and that had a geometric algebraic multiplicity of 2, 1, 1, and then you computed your eigenvectors for each of these eigenvalues. So suppose you obtained one eigenvector and another eigenvector and two eigenvectors here, and that's when your matrix A is diagonalizable because you obtained 4 linearly independent eigenvectors, right? And then you have 4 linearly independent eigenvectors, and then let's consider this entire space R4, and then this one can work as kind of a basis that represents any point in this R4, right? So we consider this kind of a B coordinate thing that we learned, okay? Okay, and then suppose that one is V1, V2, V3, and V4. And then suppose the vector x, vector x is represented by using this new basis vector, which means, so suppose you want to obtain the new coordinate or coefficient that is represented as the linear combinations of our new bases that represent any point in R4. Okay, and then in that case, how do we compute that? So given the vector x we obtain, so we basically solve this guy. C1, C2, C3, C4. So these four coefficients are corresponding to the linear combination coefficient of this V1, V2, V3, and V4. Right? So here, so let's consider the diagonalizable situation. In that case, this, let's call this matrix as V, and then this V will have the inverse, right? And then this new coordinate can be represented simply as V inverse and X, right? Okay, so it's like changing the coordinate system from the standard coordinate system, like X, Y, Z, and W, and then we change the coordinate into new coordinate vector in terms of your eigenvectors as the new basis vectors. Okay, and that's the meaning of the C. And then let's get back to this this similarity transformation. In this case, suppose you are transforming this vector x, okay, and then P inverse is here, so P is the same as V, and then P inverse of x times x, so that is the new coordinate based on your eigenvectors, okay. And then what do we do by multiplying D? You just scale them up with these new the diagonal entries, okay. So suppose D was 3 and 2 and 0, 0, and then you just multiply the first coordinate by 3 and the second coordinate by 2, and then you represent this result back by using this matrix P. Okay. Okay, so time is already up. So it's like a really interesting kind of relationship. So yeah, let me have just one more minute. So you basically send the original vector x to a new vector, new coordinates by using your eigenvectors. Okay, and then from in that space, you can simply just scale each of these elements by using the diagonal entries. Okay, but in the case of general matrix vector multiplication, and then it will have all these values in here, right? All these non-zero values in here, right? So these kind of a matrix vector multiplication will be really complicated. You have to compute this inner product between row and column and so on. But if this matrix is diagonal, and then it's really simple. So you can just multiply. So in this case, 3, 0, 0, 2 times maybe 5 and 8. And then this computation will be 3 times 5 and 2 times 8. So it's really simple. And then you multiply P again. It means, so you sent one vector into a new coordinate that is based on your eigenvectors, and then the scale each elements using this diagonal matrix, and then send the resulting matrix back to the original space. So that's the meaning of this multiplication of matrix P. Okay, so yeah, sorry for the delay. Okay, so that's it for today's class, and also the end of our semester. And yeah, there is no additional homework, but I will give you. I send the list of problems that you can solve just like a homework for your kind of training purpose. And then again, our exam will be next Tuesday at 10:30. Okay, and exactly in this class. Okay, that's it for today's class. Thank you very much for.
시험 범위는 전범인가요?
범위는 전범이에요. Yeah. So the exam scope will be the entire content that we learned.
5-몇 가지
네?
정확하게 5-몇 가지
5-3. 5장은 1, 2, 3. 그리고 6장도 들어가고요. 네, 하여튼 수고했고요. 한 학기 동안 고생 많았어요. 네.
이게 U가 매트릭스고 X가 벡터, X가 벡터잖아요.
네.
그러면 UX하면 이런 벡터가 나오고 이렇게 해도 X 벡터가 나와서 이 두 개를 합하면 스칼라가 나오는 거예요. 그래서 우리가 더했는지
이게
어떻게 이게 다 더해지는 건지
네. 그러니까 그게 거기서는 내가 좀 채점을 좀 스트릭트하게 했는데 U가 지금 이렇게 생겼죠. 그래서 U가 일단은 이렇게 세 개가 있다고 쳐봐요. 그러면 X는 이게 3개짜리 숫자를 가진 컬럼 컬럼 벡터일 거라고. 그죠? 그러면 이게 U1, U2, U3라 그러면 이건 X1, X2, X3라 그러면요. 그럼 이거는 자, 방금 했던 것처럼 그러니까 이게 하나가 리니어 컨비네이션 코에피션트로 쓰여요. 요 U1, U2, U3. 그러면 결론적으로는 벡터 하나가 나오고요. 그죠?
왜요?
왜냐하면 이 리니어 컨비네이션 그러니까 2개짜리로
네,
하면
벡터 하나가 나오죠.
벡터 하나가 나오죠?
네.
벡터 하나가 나오고 그 벡터가 어떻게 표현이 돼야 되느냐? U1, 요거 벡터예요. 여기다가 X1, 그죠? 플러스 X2, U2 이렇게 돼야 되죠. 즉, 이 벡터의 스케일링을 이렇게 해갖고 이거를 더해준 형태로 이 싱글 벡터로 나와야 돼요. 근데 지금 여기서 이렇게 썼다는 건요. 이게 첫 번째 벡터고요. 이게 두 번째 벡터. 즉 UX가 이렇게 쓴 거예요. 지금 X1 equals times U1 그 다음엔 X2 times U2 이런 식으로 매트릭스로 형태로 썼다는 이야기예요. 지금 이 형태는 맞죠? 그렇기 때문에 틀린 거예요.
근데 얘가 U가 n by n이면은 X도 n by 1이 되잖아요.
네, X가 n by 1이 될 때
그러면 이게 n by 1이 돼야 되는데
n by 1이 돼야 돼요.
무슨 말에 의하면 1
네, 이게 n by 1이죠. 이게 n by 1이지만 이거는 이제 뭐 여전히 n by 1이 아니라 여기서 이렇게 썼다는 거는 이 컬럼의 개수가 여러 개란 뜻이잖아요. 그죠? 그랬기 때문에 이게 틀린 거예요. 그러니까 얘는 한 벡터로 나타내줘야 돼요. 근데 지금 이렇게 썼다는 거는
그럼 밑에 이렇게 쓰면 안 돼요?
여기서 이미 틀린 거예요, 지금. 네, 여기서. 왜냐하면 이거를 벡터로 이렇게 나타냈다는 거는 여전히 UX를 매트릭스로 지금 보고 있다는 거거든요. 맞죠?
그럼 만약에 이거를 제외하고 이 밑에 과정은 맞는 거예요?
이 밑에 과정도 틀리죠. 네. 왜냐하면 그러니까 이거 더하기로 쓰여져야 돼요. 이게 트랜스포즈가 된 것도 지금 이것도 답이 아니에요. 그러니까 이걸 트랜스포즈를 했기 때문에 이게 나왔다는 거고 그 말은 이거를 여전히 매트릭스로 보고 있기 때문에 그렇다는 거거든요. 네, 그래서 이거 같은 경우 이런 거 같은 경우는 좀 개념을 좀 잘 잡아야 된다라고 생각을 해갖고 왜냐하면 매트릭스와 이렇게 벡터 간에 곱해졌을 때 네. 사이즈나 이런 문제가 굉장히 좀 중요한 이슈이기 때문에 저거는